One of the more useful elements in electronics is a capacitor, and its purpose is to both separate and store charges. Anytime we have two conductors that aren't touching, we can think of them as a capacitor. And there may be situations where we don't really want something to be a capacitor, but it acts like one anyway. The capacitor can have any shape, but the simplest one and the one we'll use the most is a parallel plate capacitor, which is just what it sounds like. It's two conducting plates that are parallel to each other. If we connect one to the positive terminal of a battery and the other to the negative terminal of a battery, positive charges will flow on to the plate connected to the positive terminal and negative charges on the other one. The ability of conductors to separate and store charge like this is called capacitance. The most important equation when we're discussing this, and this is kind of like F equals ma from last semester, is Q equals CV. Here, V is the potential difference between the plates. C is the capacitance. This is measured in farads, and it's a capital F symbol because it's from Michael Faraday's name. And Q is the charge on one of the plates. And whenever we talk about the charge on a capacitor, we just mean the absolute value of the charge on one plate. Since in general they'll have opposite charges on each plate, we would never talk about the total charge by adding the two plates because then we'll get zero whether there's any charge separation or not. Below we have a selection of capacitors. These are in things like your computer, your microwave, all sorts of electrical and electronic things. These larger ones here, this is maybe the size of one of the knuckles on your little finger. These smaller ones, this is about the size of an M&M, more or less. These things that have these vanes that actually open and close, these are variable capacitors, so you have some options when you, depending on how you twist it. There are much smaller capacitors available. What you would find inside your phone if you opened it and you could recognize it, they would be this size or smaller because they can be really incredibly tiny. Now, if we want to go into the business of making capacitors, we need to know the connection between the materials, geometry, and capacitance. This depends on the shape of our capacitor, for one. So again, we're going to stick with the easy parallel plate design. Physically, it would look like this. We have plate area A, separation D, we connect it to a battery. Now, this is a nice drawing, but we can't do this every time we want to draw an electric circuit, or it'll take a football field worth of paper and all day to draw it if we hire a professional artist. So we have much simpler symbols in electrical schematics. The capacitor is just this pair of parallel lines. Now, technically, a battery is a collection of cells, where the cell is where the chemical reaction is happening. The cell is also two parallel lines, but there's one long and one short, where the long one is positive, the short one is negative. A battery is a set of alternating long and short lines, like this. Notice the long one here, positive, negative, positive, negative. These are stacked in series. Now, a battery is a set of these things, but if you look closely at the labels, some things that we call batteries, like AA, AAA, C, and D, really say dry cell or alkaline cell or something like that. The 9-volt says battery because it really is a battery. It's a collection of 6 of these cells. Usually I'm going to be lazy and just put one short line, one long line, and whatever number I want for voltage, whether there's an actual chemical reaction that will give us that voltage or not. That's not really important for us since we don't design batteries for a living. So the picture above would look like this in a more realistic setting, where we have a capacitor here, battery here. If we assume that the plates of the capacitor are infinitely large, we already know from our work with Gauss's law that the electric field between them would be uniform and given by sigma over epsilon naught, where sigma is the surface charge density on the plates and epsilon naught is the permittivity of free space. If the field is uniform and the distance between the plates is d, we can write the voltage difference between the plates as this integral that we saw before. This is a path integral for E. E only has a component in the direction, If we assume that the plates in the capacitor are infinitely large, we know that the electric field between them is uniform and it's given by sigma, the surface charge density, divided by epsilon naught, the permittivity of free space. If the field is uniform and the distance between the plates is d, our voltage difference, the path integral of the electric field, gets much simpler. E comes outside the integral. All the motion that matters is in the direction of E, so the dot product goes away, and we just need to integrate the distance from one plate to the next, which we've already said is little d. So we can say the voltage difference between the plates must be sigma d over epsilon naught. Remember that the definition of sigma is Q over A, so we can write V equals QD over A epsilon naught. However, we also know from our main equation that Q equals CV, so we could solve this for C, and we get C as A epsilon naught over D. Now, to see that there's really a lot more than this going on in the engineering of a modern capacitor, we can imagine designing one that's 100 microfarads. This is easily available for a few pennies. We start with plates that are huge, just to see how difficult this is going to be, with an area of 1 square meter, so about the size of a window or a kitchen table or something. We put them close together with a separation of 1 millimeter. If we have air between the plates, the permittivity is really close to vacuum permittivity, so we can just use it. The math is pretty simple. We put in the area, the plate separation, and this permittivity constant, and we get 8.85 nanofarads, which is very far from where we need to be. This is tiny. We can't really make the plates much larger because they're already ridiculously large at 1 square meter, but what if we try and make the D smaller? That will also increase the capacitance. If we wanted to make D equal to 10 to the negative 6 meters, which is about 1% the thickness of a hair, by the way, and not much larger than the wavelength of light, that only gets us up by a factor of 1,000 to 8.85 microfarads. Now, besides the fact that we can't manufacture two 1 by 1 meter plates that are a micrometer away from each other and keep them free from dust or anything else that would bridge the gap and connect them, we can work out the electric field strength. Let's say we connect this giant capacitor to a 5-volt source. Our field strength is then going to be 5 volts divided by 1 micrometer, or 5 million volts per meter. This is more than enough to ionize the air, so this must not be how we make real capacitors. What we really do is put a material between the plates known as a dielectric. It's basically an insulator, but the main thing for us is how well it polarizes. That means how well can we get the bound electrons on the atoms to go upstream a little bit in the electric field and leave the positively charged nuclei behind. Now, this is a very, very small displacement. We're talking about much smaller than a nanometer. But when we do this on the scale of a physical object, if they all move, so I've put positive charges here on this picture in your book for the top plate of a capacitor and negative charges here on the bottom, what that would do, the electrons on these atoms are going to be preferentially pulled up to the top a little bit, tiny amount. Same thing for all the rest of them, and that will leave these nuclei here down below where they would be otherwise by, again, a tiny amount. That gives us an electric field that opposes the electric field from these green charges that we put on the plates. The two electric fields act to partially cancel one another, and the difference in the total field and the field without the dielectric we call kappa. That's not a K, and it's certainly not the Coulomb's law K. It's field strength without the dielectric divided by field strength with the dielectric. This is dimensionless, and we call this the dielectric constant. We can use this to write a new capacitor manufacturing formula as A kappa epsilon naught over D. And we could also write this kappa epsilon naught as just epsilon, where this is a material-dependent permittivity rather than permittivity of free space. If we use this, we need to know values of kappa for various materials, and for a vacuum, kappa is 1. For dry air, it's very, very close to that. It's 1.0006, and you'll see numbers over 250,000 for some specialized compounds. What this lets you do is make 1 farad capacitors that you can hold in your hand and pay a couple of dollars for. Now, in the past, 30 years ago, a 1 farad capacitor would have had to be moved by forklift, and it would have cost a fortune. These materials that we put in the capacitor, though, have their own dielectric breakdown voltages, so we can destroy them if we crank the voltage up enough. We can find the capacitance of other arrangements of conductors, and calculating this from first principles is in general very, very hard, kind of like finding the electric field from a very weirdly shaped thing like a charged person. However, if we have a highly symmetric arrangement, we can put Gauss's law to work and figure out the capacitance that way. The one example we'll do besides parallel plate, let's say we have a wire inside a cylinder and we use Gauss's law to find the E field between them. We already know what we're going to get. If we have a line charge, we don't care about the cylinder's charge. If we're in between them, all that matters is the enclosed volume, which would just be the line charge. The answer to that we got a couple of chapters ago, and it's Q over 2 pi epsilon naught RL, or lambda over 2 pi r epsilon naught. If we integrate that from the wire at the center out to the edge, which is the cylinder, that's a radial integral. We're moving in the dr direction. That's not a hard integral. We do that and we get a natural log. But notice we still have our Q equals CV, so we can use that to pick out what the capacitance is for this arrangement of conductors. It's 2 pi epsilon naught L over natural log outer radius over inner radius. This is what's called a coaxial cable, and if you're thinking, does this have any real-world applications? If you get cable internet or cable TV, this is how it gets piped to your house. If you've ever looked at it before you screw it into the modem, there's a central copper wire, then there's some insulation, which is your dielectric, and it's usually white Teflon, something like that. Outside that, you have a braided metal sheath. I think it's aluminum. The whole thing then gets covered up in plastic just so it doesn't get damaged. One of the physical properties you can look up if you're going to buy some of this, the seller will tell you what the capacitance per length is, and for TV cable it's usually in the 50 to 100 picofarads per meter range.